Welcome to Module 2 of the course, where we're going to be examining some of the different pieces and parts that make up our networks. Specifically, we're going to be taking a look at things such as switches, routers, wireless access points, firewalls, intrusion detection and prevention appliances, and many, many more. And we're going to get started in our next video by going back in time a little bit to relive the glory days of analog modems. I'll see you there. In this video, we're going to take a look at a legacy way of transmitting data across the PSTN, the Public Switched Telephone Network. And I say it's a legacy technology. It is still in very limited use today. What I'm speaking of is an analog modem. When I got my first analog modem back in the 1980s, it was a 300 baud modem. It transmitted data at 300 bits per second. And speeds have come a long way since then. From there, we went to maybe 2400 bits per second, then 9600 bits per second, 14.4K, 28.8K, 56K modems. And let's take a look in this video at how that works. When the PC is transmitting the data to its modem, be it an internal modem or an external modem, it's doing it digitally. It's sending ones and zeros, where maybe a binary 1 is the presence of voltage and a binary 0 is the absence of voltage. And once those binary bits are sent into the modem needs to convert that into tones that can be sent over the PSTN. So these analog tones will be sent from one modem to the far end modem. Then that far end modem does the demodulation of the modulation-demodulation. It converts this analog waveform back into ones and zeros and sends it to its destination. And I've used a couple of different terms here in this video, and I want us to distinguish between them because there is a lot of confusion about this. I talked about baud, and I talked about bits per second. Those are not necessarily the same thing. For example, baud represents the number of tone changes per second. That's how, with an analog waveform, we can represent binary ones and zeros based on the number of tone changes. And I said that I had a 300 baud modem that transmitted at 300 bits per second. So in that case, the baud and the bits per second, those were equal, but they're not necessarily going to be equal. Because bits per second, that's the number of ones and zeros that we can transmit over a line. The challenge comes in when we try to have more and more and more tone changes per second. If that number gets higher and higher and higher, then the number of tone changes might not be generated correctly by the source modem such that they can be interpreted by the destination modem. So let's take a look at how we get some of those higher speeds. In the example I gave you, I said I had a 300 baud modem and it transmitted data at 300 bits per second. And in that case, there were 300 tone changes per second. But notice we're only using one channel because we could send multiple frequencies over the PSTN, but here I'm just using one channel and I'm saying we're changing between this tone and this tone, this tone and this tone. That's one channel. We could bump it up such that we have 2400 tone changes per second. That would be 2400 baud. That would give us 2400 bits per second if we were using one channel. But what if we used more channels? We could stay at 2400 baud, we could have 2400 changes in tone per second, but we could use multiple channels. One channel might be using these two frequencies that it goes back and forth between. Another channel could be using different frequencies. So if we had 4 channels, each of those channels doing 2400 tone changes per second, that's still 2400 baud on 4 channels, but it gives us 9600 bits per second of throughput. Let's jump up a bit more. Maybe we have 2400 baud still, but we're using 12 channels. That would let us have a throughput of 28.8 kilobits per second. Still fairly slow speeds by today's standards, but this is a technology I want you to know about: traditional analog modems. In this video, we're going to distinguish between a couple of terms that could get confused, and those are CSMA-CD and CSMA-CA. First, let's consider CSMA-CD, which stands for Carrier Sense Multiple Access with Collision Detection. And to illustrate what's going on here, consider a really old Ethernet network. This is representative of the very first network that I worked on back in the 1980s, where we had this coaxial cable running around the floor of a building. It would go from one room to the next, and if a device wanted to get on the network, they would tap in to this coaxial cable. and that was called an Ethernet bus. We didn't have RJ45 connectors that we plugged into a switch or even a hub. We actually tapped in to this cable. And a rule for transmitting on the network was that on this bus or on this Ethernet segment, we could only have one packet at a time. Because if two packets were transmitted simultaneously, they would collide with each other. In other words, they would corrupt one another. And in order to prevent that, these devices ran CSMA CD. And here's what that means. The carrier sense means that we can listen to the wire to see if anybody else is transmitting, because if they are, we know we cannot transmit. Only one packet allowed at any one time. The multiple access means that we can have multiple devices connected to this wire, and any device can talk at any time, as long as nobody else is talking right then. And if a collision does happen, we can detect that. So let's say that these two PCs on the bottom of the wire, they both want to transmit, and they both listen to the wire at the same time. They hear the same period of silence, and they both simultaneously conclude it must be safe to transmit. And they transmit and their packets collide, and they're corrupted. Well, the way they would detect that collision is that on an Ethernet bus, there would be a spike in voltage that would be detected by the PCs, and they would realize, uh-oh, I tried to transmit, somebody else tried to transmit at the same time, our packets collided, and knowing that we still both need to transmit, what I'm going to do is set a random back-off timer. And hopefully the other PC is going to set a different random back-off timer, and we will each transmit when our timer expires, and hopefully this time avoid a collision. So let's say the PC on the bottom left sets a random back-off timer for 10 milliseconds, and the PC on the bottom right sets a random back-off timer for 20 milliseconds. So now they should not collide because they're going to wait these random amount of times, and assuming those random times are not equal, they should not collide with one another. Now that's the way it worked on an Ethernet bus, but then as time went on in the early 1990s, Ethernet hubs were very popular. We were still using CSMA CD, however. This was physically a star topology where everything starred out from this centralized hub, but logically it still worked like that Ethernet bus. We still had the rule that only one packet was allowed on this infrastructure at any one time. And when laptop 1 sent a packet maybe to the printer, it would go everywhere because the hub did not know how to intelligently forward packets. But let's say both laptops tried to transmit at the same time. Again, we would have a collision. The thing that's slightly different here, though, with a hub is that instead of seeing a voltage spike on the wire like we would with an Ethernet bus, the hub would notice there was a collision, and it would alert everybody connected to the hub by sending out a jam signal. And this jam signal said, hey, there was just a collision on the wire. If you just transmitted, your packet probably did not make it. You might want to set a random back-off timer and try again. And CSMA CD required that devices be connected using half duplex, meaning they could not transmit and receive simultaneously. They could do one or the other, because if they were doing both simultaneously, that could be two packets on the wire. We don't use CSMA CD very much these days because we're typically connecting with full duplex connections into an Ethernet switch where we don't have that collision issue. But we do see CSMA CA in today's networks, carrier sense multiple access with collision avoidance. We might see this in a wireless network, and the goal is essentially the same. On a wireless access point, we may have a limit of one transmission at any one time. And that's certainly developed over the years, and there are now technologies that allow us to have multiple antennas and multiple streams at one time. But in its basic form, a wireless access point can only be talking to one device at any one time. So what CSMA CA does is allow, let's say, client 2 to listen to the airwaves before it transmits. Let's say client 1 is transmitting to that wireless access point, but in addition to sending the radio waves to the wireless access point, client 2 hears those radio waves, and it's going to wait its turn. You see, when client 1 sends out the radio waves, it doesn't just go to the access point. It's received, hopefully, by client 2. And client 2 that wants to transmit, it's going to see that signal coming in from client 1. It's going to say, somebody's talking, I need to set a random back-off timer, and then I'll try again after that timer expires. A challenge that can happen, though, is let's say that client 1 is to the left of this access point such that it's just barely in range. It's very far off from this access point. The access point can receive the signal, but client 2 is very far to the right of this access point. So just because the access point can see client 1's transmission, that does not mean that client 2 can see the transmission. It might fade out before it gets to client 2. This is called a hidden node problem. This is where client 2 listened to the airwaves and it incorrectly concluded that nobody else was talking at that moment, and then it transmitted. That could lead to a collision. And we're not going to be able to detect that there was a collision by listening to something like the voltage on the wire. There is no wire. But we try to avoid a collision by listening to the airwaves before transmitting. And we can have some upper layer protocols that can let us know if there was some missed packets and then retransmit any packets that were corrupted. In this video, we want to distinguish between a hub, a switch, and a router. And an Ethernet hub is a legacy device. Hopefully we don't have these in our network today, but the hub was the evolution of an Ethernet bus, where devices would tap into a coaxial cable. With an Ethernet hub, we could use networking cable with an RJ45 connector on the end to plug into the hub. However, the hub is not intelligent in how it forwards traffic. Sometimes it's called a bit splitter because it will receive traffic coming in on one port, and having no idea where the traffic is destined, it will replicate and then send out copies of those received bits out all of its other ports. It's making sure that everybody gets the transmission, but it has no idea who is supposed to receive the transmission. And the restriction that an Ethernet hub creates is that we have to run carrier sense multiple access with collision detection, or CSMA CD for short, and that's in an attempt to prevent any two devices from transmitting simultaneously, which could result in a collision. However, during the 1990s, there was a migration from Ethernet hubs to Ethernet switches. Ethernet switches can make intelligent forwarding decisions. An Ethernet switch is going to learn what MAC addresses live off of which of its ports, and then when it receives a frame, it's going to take a look at that destination MAC address, and it's going to check its MAC address table that it constructed and say, do I know where this device lives? If so, I'm just going to send it out that port. So let's go through a scenario here. Let's say that laptop 1 wants to print to the printer. Now, laptop 1 has a MAC address that's a 48-bit address that is burned into the network interface card of our network clients, and it's written in hexadecimal notation, and we'll pretend that laptop 1 has a MAC address of all A's, and it wants to talk to the printer that has a MAC address of all C's. So when the frame is sent from laptop 1, it's got a source MAC address of all A's, it's got a destination MAC address of all C's, but the switch has just powered on, it has no clue where any of these MAC addresses live. So when it first receives that frame coming in from laptop 1, since it has not yet learned where the all C's MAC address lives, it's going to do what is called flooding. Flooding is when we receive traffic on one switch port, and then we send copies of those frames out of all other switch ports. Flooding is what we would do when we don't know where the destination MAC address lives. However, when that frame comes in from laptop 1, the switch is going to take a look at the source MAC address, and it's going to say, I just learned something. The all A's MAC address lives off of interface gigabit 1. So if anybody else wants to communicate to the all A's MAC address, I'll just send those frames out of gigabit 1. And the printer is now going to respond to laptop 1, and when it does, its source MAC address is all C's, and the destination MAC address is the all A's MAC address of laptop 1. When that comes into the switch learns something else. It now knows that the all C's MAC address lives off of gigabit 3. In the future, when laptop 1 wants to talk to the printer, the switch is only going to forward traffic destined for the printer out of interface gig 3 because it knows where the all C's MAC address lives. Let's say that laptop 2 wants to communicate with the server. Same thing here. Initially, the switch does not know where the all D's MAC address resides, so it floods that frame out of all other ports. And when it does make it to the server, and it learns a couple of things. It learned from that frame coming in on gig 2 that the all B's MAC address lived off of gig 2, and then when the server responded to the laptop, it learned that the all D's MAC address lived off of gig 4. Now, this switch has a fully populated MAC address table, so any device can talk directly to any other device without having to flood that traffic everywhere as a hub would do. And as an example of what an Ethernet switch might look like, here is an Ethernet switch model, a Cisco Catalyst 3650 switch. And on enterprise class switches like this, you typically have a fairly high port density. Here we've got about 48 ports into which we might be connecting our clients. And then you can see over on the right-hand side, we have some uplinks to connect us to other switches, and those speeds could be a whopping 40 gigabits per second. But that's a look at an Ethernet switch. Next, let's consider a router. A router is going to get packets between different network segments. In other words, different subnets or different VLANs, we might say. And the way the router does that is it has an IP routing table. It could have an IP routing table for IP version 4. It could have another one for IP version 6. But as an example, let's consider this IP version 4 routing table that our router has. The laptop wants to send traffic to the server, and the server's IP address is 192.168.1.200. That's the destination IP address in this packet. When the laptop sends the packet to its default gateway, which is the router is going to check its IP routing table, and it's going to say, oh yeah, I've got a connection to the 192.168.1.0/24 network, and the return traffic comes back from the server, back to 10.1.1.100, and the router forwards that out of gig 2. The router knows where both of those networks live, the one where the laptop resides and the one where the server resides. However, sometimes we might be going out to the internet, which contains hundreds of thousands of routes. Does the router have to know about those 900,000 routes or so that exist on the internet? And the answer is maybe not, because the router can have something called a default route. Do you notice the network of 0.0.0.0/0? That's called a default route entry, which means if you don't have more specific route information to get to a certain IP address, go here. So let's say we're trying to go out to some device on the internet, and its IP address does not belong to the networks known to our IP routing table. In that event, when this laptop wants to go to the internet, the router is going to say, I have no clue where this IP address lives, so I'm going to send it out to the internet. That's my default route, which is where I'm going to send everything if I don't have more specific information about that destination. And that's a look at how a router can forward packets based on its routing table. But that brings up the question, how does the router get its routing table populated? There are a few different ways. The router may be directly connected to a network. That's a way for it to know that this network lives here. That's what we see in this router with gig 2 and gig 3. We're directly connected on gig 2 to the 10.1.1.0/24 network. And on gig 3, we're directly connected to the 192.168.1.0/24 network. So those networks live in this router's IP routing table. Maybe we go in and we statically configure a route. Maybe we, as an administrator, as an example, went in and statically configured that default route, where we said, if you don't have a more specific route entry, then just go to the internet. Or in an enterprise network where we might have multiple routers and multiple paths between those routers for redundancy and maybe for load balancing, we could run a dynamic routing protocol. The dynamic routing protocol is going to respond to changing network conditions. So if a link goes down, that dynamic routing protocol is hopefully going to reroute us through another path. Examples of dynamic routing protocols you might hear about include RIP, OSPF, EIGRP, ISIS, or maybe BGP, which is a dynamic routing protocol used on the internet. Another way that a route could be added to a router's IP routing table is that it could be redistributed from another routing source. Maybe we're connecting a couple of companies together, and one company knows about these networks and they run one dynamic routing protocol, and the other company knows about these other networks and they run a different dynamic routing protocol. Well, we could configure redistribution on the router that joins those two networks together and redistribute routes from one routing protocol into the other and vice versa. Here's an example of what a router might look like. And there are different form factors for routers. Here we see a Cisco 4431 router, and it has a few Ethernet interfaces that could connect us to different subnets. But one thing we see on a router that we often don't see on a switch is we have more flexibility than just having Ethernet connections. For example, this particular router has some digital circuit ports. If we're connecting out to a T1 or an E1, which are digital circuits that go back to a telephone central office oftentimes, we could connect those digital circuits into this router. If we had a traditional analog telephone that might be in your home, we could connect that into this router because this router has an FXS port, a foreign exchange station port. And I don't want you to take time trying to memorize what those different ports are. I just want you to understand that a router may have more ports than just Ethernet ports because it tends to be more flexible than a switch. In this video, we want to distinguish between a collision domain and a broadcast domain. First, consider a collision domain. This is a network segment, and on that network segment, we can only have one packet at any one time. And to visualize this, let's go way back in time to the original Ethernet bus, where we had end stations connecting into a coaxial cable that kind of ran around an office floor, and we would tap into that coaxial cable. All of these devices live on the same collision domain. You might recall that on this Ethernet bus, we're running something called CSMA CD, Carrier Sense Multiple Access with Collision Detection. We're listening to the wire in hopes that nobody else is transmitting at that moment, because we're all on the same collision domain. We can only have one frame on the wire at any one time. But let's say those two bottom PCs, they're listening to the same period of silence and they simultaneously transmit. That creates a collision. And the reason that collision was possible was because those devices were on the same collision domain. And these Ethernet bus networks back in the 1990s were replaced in large part by Ethernet hubs. However, even though we are physically connected as a star topology with an Ethernet hub, logically, we're still acting like that bus. We're still running CSMA CD. And I want you to know that all ports on a hub belong to one and only one collision domain, because a hub does not make intelligent forwarding decisions as a result of not knowing where anybody lives. It just replicates any bits that it receives on one port out all other ports. And as a result, only one device can communicate at any one time. So a bus is one collision domain, a hub is one collision domain. What about an Ethernet switch? Well, it gets a lot better with an Ethernet switch. With an Ethernet switch, each port is in its own collision domain. For example, if laptop 1 wanted to talk to the printer at the same time that laptop 2 is talking to the server, that's totally fine, because the switch is not going to take that frame coming from laptop 1 going to the printer. It's not going to flood that out to laptop 2 in the server as long as it has learned where that printer lives. So each port on a switch, I want you to know, belongs to its own collision domain. As a benefit, besides more traffic simultaneously on the network, we can run these devices in full duplex mode, where we can transmit and receive simultaneously. If we're using a hub, we can only use half duplex mode, where we can transmit or receive at any one time, but not at the same time. Next, let's consider a broadcast domain. A broadcast domain is a portion of the network throughout which a broadcast will travel. So let's say that a PC boots up and it wants to get an IP address. A way that it can do that is by sending out a DHCP discover broadcast to say, hey, are there any DHCP servers out there that can give me some IP address information? Since we might not know where that DHCP server lives, we send out a broadcast throughout this broadcast domain. And on a hub, if a broadcast comes in on one port, it's going to be replicated out all other ports. No surprise. That's what hubs do. They receive bits in on one port and they send those out all other ports because the hubs have no idea where the end stations live. But what about a switch? With a switch, by default, all of these ports on a switch, they belong to one broadcast domain. If laptop 1 sends out a broadcast, maybe looking for a DHCP server, the switch is going to flood that out all other ports. Does that seem a little unswitch-like? Well, what's going on here is a broadcast has a destination MAC address of all Fs in hexadecimal, and the switch is never going to learn a MAC address of all Fs. So it's always going to appear as an unknown destination, and as a result, it's going to flood it throughout the broadcast domain, which is a good thing. We want broadcast to be able to reach devices that it needs to reach within the subnet. But this is not going to be terribly scalable. If there were a lot of broadcast traffic, that could start to cause a problem because every device in this broadcast domain gets the broadcast. If it's not destined for that device, the device still has to take time out of its day, look at the packet and say, oh, this is a broadcast, it's not for me, discard. We don't want to have too much broadcast traffic on a network. So the question is, what breaks up a broadcast domain? And the answer is a router. A router is going to interconnect broadcast domains, also known as subnets or VLANs. And with a router, each port is connected to a different subnet. And each subnet is a broadcast domain. So let's say that the laptop on the left is going to try to reach a D8CP server, and it sends out a D8CP Discover broadcast. Well, here's what happens by default. By default, that router is going to say, you're sending a broadcast. I'm not going to forward a broadcast. And the router is going to discard that packet because a router is going to break up broadcast domains. So in this example, we have 3 gigabit Ethernet ports on a router, and that means we have 3 broadcast domains on this router. We might have several different types of mobile devices in our network, such as a smartphone connecting into our network, maybe a laptop that we're carrying from one office to another office. How is that mobility possible? Well, it's thanks to wireless technologies. And these wireless clients, they can connect to wireless access points. And this is their pathway out to the rest of the world. And this wireless access point is going to contain one or more antennas for communicating with these wireless devices. And even though we won't get into it in this video, there are different bands of frequencies that we can have used by those wireless access points. And each band has different channels, and we want to avoid overlapping channels so that one access point isn't interfering with another access point, because in larger environments, you probably want to have lots of access points spread throughout your building, or maybe spread throughout your campus, so somebody can be mobile and they never lose connectivity with the network. And this wireless client is going to get to the rest of the world through this wireless access point, because they typically have one or more connections out to an Ethernet network. And there are different types of wireless access points out there with different numbers of antennas in them. But just as one reference, here is an access point that's pretty popular out there, and it's a Cisco access point you might have seen mounted to the ceiling in different buildings. I've seen these types of access points mounted to the ceilings in buildings like hotels, for example. And that's a look at a wireless access point, which can give a mobile device connectivity into the rest of the world. The purpose and life of a network firewall is, in general, to protect our inside network, like our company, from an outside threat, like the internet. And the term firewall comes from a structural firewall you might see in a building, such that if there is a fire in one area of the building, the firewall is there to prevent that fire from spreading into another area of the building. That's basically what the network firewall is doing. It's trying to protect one area of our network, such as our company's network, from another area of the network that might present danger, such as the internet. We might have an attacker out on the internet trying to attack our network and sending malicious traffic into our network. We want that firewall to intercept that malicious traffic and drop it. And there are different types of firewalls that I want you to know about. One type of firewall, and I hesitate to even call it a firewall because it's very rudimentary, it's called a packet filter. And a packet filter is essentially a rule or a set of rules that says this source is allowed to go to this destination using this particular protocol. And we might have a rule that said anybody on the inside of our network can go out to the internet using any protocol, but we don't want people on the internet to come back into our company. Now, at first glance, that might seem like a good thing, but let's say that PC1 on screen is trying to go to a web server on the internet. Well, it sends that request out to the internet for a web page. The firewall allows that request through because the source was PC1. It's on our trusted inside network. But what happens when that web server tries to send back the requested web page? The firewall looks at that packet and says, no, the source IP address on this packet is on the internet. I don't trust the internet. I'm going to drop that. So PC1's traffic to the web server gets to the web server, but the return traffic is dropped. How do we fix that? With a stateful firewall. With a stateful firewall, this firewall does what is referred to as packet inspection. It still wants to trust the inside network and not trust the outside network, But if traffic originated on the inside of the network, like from PC1 going out to the internet, the firewall is going to inspect that traffic originating on our trusted inside network, and it's going to make a note of things like this source IP address on the inside network is going to this destination IP address on the internet, and we're using this particular protocol with these particular port numbers. And it remembers that information. So in my example, when the web server is sending the return traffic back, the firewall says, oh, I think this is return traffic. It wasn't originated on the internet. It was originated on the inside of the network because I inspected a packet that had these IP addresses transposed and these protocol port numbers transposed. So I conclude this is safe return traffic. That's a stateful firewall. And we might hear a modern day firewall referred to as a next generation firewall or an NGFW, sometimes called a layer 7 or an application layer firewall. Here we can do deep packet inspection and recognize data types that we might not want to allow to leave our company, maybe sensitive employee information. Under no circumstance do we want to send that out to the internet. We could block that by doing deep packet inspection. We can also go check an internet-based database of current threats. And based on that database of current threats, we're going to be able to better recognize malicious traffic as it is coming in from the internet. We'll say this sequence of packets is matching this signature of a known malicious attack. We're going to block that traffic. And in this example, notice that firewall only has a couple of interfaces, one going to the internet, one going to our inside network. However, we might have some servers at our site that we want to be accessible from the internet. Maybe we have a web server. Maybe we have a corporate email server, and we want both of those servers to be accessible from internet users. So what can we do? We can have another zone. We can have an outside zone that connects out to the internet. We can have an inside zone that connects to our inside corporate network. But for those devices that we do want to be accessible from the internet, we can put them in a zone called a DMZ, a demilitarized zone. So even if somebody from the internet did compromise the web server, they would not be able to use that as a hopping off point to get into our inside network because the inside network is protected from the DMZ. And this is when we have servers at our site. But more and more people are putting their servers in the cloud. Is there a way to have a firewall protection for servers that live in the cloud? There absolutely is, because we can have virtualized firewalls. Just like we can install a virtual server on Amazon Web Services, we can install a virtual firewall that logically sits in front of that server and protects that server virtually from malicious traffic. And that's a look at a network firewall. There are so many different types of attacks that someone could launch against our network from the internet. So for security purposes, it would be super useful if we could maintain some sort of a database of well-known attacks where we could recognize the signature of a well-known attack based on the pattern of packets coming in. And we have a couple of network appliances we're going to discuss in this video that can do that. They can analyze packets and see if they match a recognized signature. And if we do have a match, we can take action to stop that attack. And those two appliances are an IDS sensor, or Intrusion Detection System sensor, and an IPS sensor, an Intrusion Prevention System sensor. First, let's consider the IDS sensor. The IDS sensor is going to get a copy of traffic and analyze that copy, while the IPS, as we're going to see, is going to be in line with the traffic. But here we have a multi-layer switch, and it's configured to mirror, in other words, to make a copy of traffic headed towards that layer 2 switch and send those packets, those copies, to the IDS sensor. And the IDS sensor is going to analyze those packets against its database of well-known attacks, which does need to be updated periodically. But let's say that somebody from the internet, they happen to be launching a malicious attack against the client. And it wasn't the type of attack that would be recognized by just a basic stateful firewall. So the attack makes it through the firewall. The multi-layer switch makes a copy, sends one copy to the client, which suffers from the potential impact of that attack. And the IDS sensor also gets a copy. The IDS sensor analyzes these packets and it says, I think we're under attack. And it can send a message to the firewall to say, I want you to start blocking this IP address that is out on the internet, because we have reason to believe that they are sending malicious traffic into the network. So dynamically, that firewall can create a rule, and when the next packet tries to come in from the internet destined for that client, the firewall says, nope, you're going to be denied, and it's going to drop that traffic. And while this is a great solution, we're protecting ourselves against many, many different types of attacks. The client actually does get hit with maybe one or two or a few packets of that attack. And there are some attacks called atomic attacks. They can do damage with just a very few number of packets, maybe even one packet. So even better than an IDS sensor, many would argue, is an IPS sensor. Because an IPS sensor doesn't just receive a copy of the traffic, it sits in line with the traffic coming in from the internet. So it can analyze the packet and say, yes, it's allowed, or no, it's not allowed, before it's even sent onto the network. Here, let's say that we're getting traffic in from the internet. Again, somebody is trying to attack our client. The IPS sensor is going to analyze it immediately and discard it. It never gets into the network. And here I did not include a firewall in the topology, but we could have. We could have an IPS sensor send updated configuration instructions to a firewall, much like the IDS sensor did. But in this case, the IPS sensor took care of blocking that traffic. So here's the distinction. An IDS sensor, it can inspect and react to a copy of the received traffic, while the IPS sensor can inspect and react to traffic in line before it ever gets an opportunity to reach a client. A virtual private network, or a VPN, can allow us to securely communicate across an untrusted network, like the internet. Maybe we're working from home as a remote client, or maybe we're traveling and we're working from a hotel room, and we want to connect in securely to our corporate office. Well, we could install some software on that client and maybe have the router back at the corporate office on the left-hand side of the screen handle all of the encryption and decryption and authentication of this incoming traffic. And the router can probably handle that just fine for maybe one remote client or maybe a few remote clients, but it's going to put a processor burden on the router. All that encryption and decryption can be very processor intensive. And that suggests if this needs to scale and handle multiple remote clients, instead of relying on the router to do all of that heavy processing, maybe we have a separate appliance and its job is to handle that processing. That's what we have with a VPN concentrator. And it might look something like this. So this remote client, it's going to try to talk to that accounting server. It's the VPN concentrator that does the encryption and decryption as the traffic comes off of the internet and goes back to the internet. And this device, because it's doing such heavy processing, typically it's a dedicated hardware appliance. And it can be the termination point, as in my example of the VPN, or it could initiate the VPN. It could be the originator. And as one end of this VPN connection, it's going to be responsible for doing the encryption and decryption of traffic that we're trying to protect. Let's say we have a server of some sort, maybe a web server that handles e-commerce traffic for our company. And to make sure that it doesn't go down and cost us all of those sales, it would be great to have a backup. And just to have some load balancing, it would be great to have other servers with identical content. But the question is, if I've got multiple servers containing the same content, and we'll pretend they're virtual servers, how do I spread the load across all of those servers? Well, one option is to use a network appliance called a load balancer. Let's say these virtual servers on screen contain identical content for a website. Well, maybe the first packet that comes in goes to the top server. The next packet goes to the middle server. The next packet goes to the bottom server. And again, these servers have identical content, so it really doesn't matter which server the packet gets forwarded to. And by doing this load balancing, that's going to take a load off of the hard drive and the processor on any single server. And a load balancer can also help out with maintenance. Let's imagine that I want to take one of those servers offline to do an upgrade on it. I need to swap out a hard drive, for example. Well, is that going to impact our performance? Maybe not. We can go into the load balancer and simply take one of those servers out of that pool of servers that we're load balancing across. And if we run a commercial on the big game, for example, and we're expecting an influx of orders to our e-commerce site, having a load balancer will help us adjust our capacity. Sometimes this is called elastic server capacity, because we can stretch that server capacity by spinning up some additional virtual servers. And then after the demand dies down, maybe a few hours after the big game, then we can take some of those virtual servers offline and not be paying our service provider for those servers. And here I'm showing you that load balancer as an appliance. It doesn't necessarily have to be an appliance. It could be a router that's configured to do load balancing, or there are even virtual load balancers. So if you have these virtual servers in a cloud like Amazon AWS, you could have a virtual load balancer installed in Amazon AWS and use it to load balance across your virtual servers. In this video, we're going to examine some networking appliances that could be used to filter out unwanted traffic. And you might already know about some of these appliances or some of the features on these appliances. First, let's think about a firewall. We know that a firewall tries to protect one area, like our enterprise network, from another area, like the internet. And a basic firewall does what is called stateful inspection. We send traffic out to the internet. The firewall memorizes the source and destination IP addresses and port numbers, and when the return traffic comes back in, it's able to recognize it and allow that traffic back in, assuming it originated on the inside of our network. But some firewalls have more features than just that basic service. And those firewalls might be called next generation firewalls, or you might see it written as a layer 7 firewall or an application layer firewall. As a few examples of what a next generation firewall might do, we might have knowledge about the nature of different applications. If I'm setting up a voice over IP phone call between a couple of IP phones, I might be using the protocol called SIP, the Session Initiation Protocol, to get the call set up. But then, once the call is set up, we start using RTP, the real-time transport protocol, to stream the actual voice back and forth between the IP phones. When that switchover happens, when we go from SIP to RTP, we may have a firewall that knows that RTP often follows SIP, and it can determine that these RTP packets that it's now seeing, they're part of that same voice session that it started inspecting when it was using the SIP protocol. This firewall might be able to do deep packet inspection and filter out data that it finds at layer 7, at the application layer, and prevent sensitive information from being leaked out to the internet, perhaps. We might have an intrusion prevention system sensor or an IPS sensor built into this firewall, where the firewall itself maintains this database of well-known attacks, and it can analyze inline traffic as it comes into the network. And if the traffic coming into the network matches the signature of a well-known attack, we can drop it in its tracks before it ever gets an opportunity to get inside of the network and do damage. And one type of attack that has made the news a lot is a ransomware attack, where perhaps you get this message on your screen that your data on your hard drive has been encrypted and you have to pay so much Bitcoin to this person in order to get the key to decrypt all of your data. It's like they're holding your data for hostage. That's why it's called ransomware. That's a type of malware, by the way. And malware can also get on your system and do bad things. And what these malicious people on the internet have been doing lately is they send their malicious traffic, their malware, their ransomware traffic coming in to infect our clients. They send that over an encrypted TLS tunnel. Now, does that just destroy our ability to analyze that traffic? I mean, after all, if I cannot read the traffic because it's all encrypted, how can I know that it's malicious? I'm just going to let it on through. Well, actually, there is something called encrypted traffic inspection, which allows us, with a very high degree of certainty, to identify malicious traffic even though it's encrypted. And when I first heard about this, it just seemed nearly impossible. How can we recognize malicious traffic if it's all scrambled up? Well, one way that some companies used to do this is they would decrypt the traffic and inspect it before they sent it on. That could pose a couple of issues. It's going to take time and resources to do all that decryption, and it might break some privacy policies to be decrypting this encrypted traffic. But with encrypted traffic inspection, what we can do is use statistical analysis with these huge data sets to recognize what is probably malicious traffic. And the best metaphor I've heard to explain this is going to a doctor's office. Maybe you're not feeling well, you go to a doctor's office and you give the doctor your symptoms. And after they hear your symptoms, they think, all right, based on this and this, and you're running a fever here, you probably have this particular illness. That's kind of what encrypted traffic inspection is doing. It's going to take characteristics of this traffic coming in and compare it against huge data sets. And these data sets have characteristics of benign traffic as well as infected traffic. For example, in a TLS session, we start off with a hello message, and that's not encrypted. It contains what are called cipher suites. A cipher suite is a list of parameters that we're going to use to negotiate the TLS connection. Well, what encrypted traffic inspection might be able to do is recognize certain cipher suite listings known to have accompanied malicious traffic, and it can also examine the lengths of the packets and the intervals between packets. If it measures the time between the arrival of two packets, and if that time is significantly different statistically, that could make that traffic suspect. An encrypted traffic inspection can oftentimes have more than a 99% accuracy rate. Another appliance I want you to know about is a content filter. And the main purpose of a content filter is to filter out traffic that might be considered objectionable. This might be something like pornography or violence or hate speech. Parents, they might install software on a computer, and that could protect their home computer from things like that. Or in a large enterprise, we might have an appliance dedicated to filter out what we consider to be objectionable traffic. And finally, I want you to know about a UTM appliance, a Unified Threat Management Appliance. This is a dedicated appliance that can combine multiple filtering functions. And different UTM appliances might have different sets of features, but as an example, we might have a UTM appliance that acts as a firewall, it acts as an IPS sensor, it protects us against malware, it can terminate a VPN connection coming in, and it can do content filtering. And that's a look at some advanced filtering appliances. In this video, we want to consider a proxy server. And a proxy server still may appear on some networks that you work with. However, it's not as needed as it once was. Back in the 1990s, I administered a proxy server at a university where I was the network administrator, and it helped us out there because we had limited bandwidth going out to the internet, and it could add a layer of security as well. But today, it's more common to have high-speed internet connectivity, and we have more advanced security appliances that can scan content coming in from the internet. But here's what a proxy server does if you happen to run into one. A proxy server is going to receive traffic coming from an inside client, and it's going to terminate that connection. And then, just like it was placing the connection itself, it's going to originate that same connection going out to the destination on the internet, like a web server. So if the web server asked, who is sending me this packet, the source IP address would be the IP address of the proxy server, not the PCs inside of the enterprise. Now, what's the advantage of doing that termination and then origination of this packet flow? Well, for one thing, that proxy server could filter the content. Maybe we want to block particular URLs as an example. A proxy server might be able to do that. And when I used it back at the university, the main reason we were using it was for caching. Because we did have limited connectivity out to the internet, if we had lots of clients booting up their computer and going to yahoo.com, for example, whatever the graphic was for the day on yahoo.com could be stored on the proxy server. That way, when the second person went to yahoo.com or wherever they were going, that graphic could be served up locally from the hard drive of the proxy server without pulling it down again from the internet. And that process was called caching. And at the time, it saved a decent percentage of bandwidth. It was definitely worth having a proxy server. However, maybe not so much today. If we do have a network with fairly high-speed connectivity out to the internet, and in order to use a proxy server, we would have to go into the browsers and point the browsers to the proxy server. So some applications may need to be configured in order to use the proxy server. However, there have been some advancements in proxies, and you may have a proxy that can operate transparently, where the apps do not have to know that there is a proxy server sitting in the middle, and the proxy server can just transparently terminate and then originate that packet flow going out to the internet.